Smriti Chaudhury, and today I'll be showing how to solve the Math Kangaroo 2024 grades 5 to 6 problems. Let's get to it. Number 1. Alina folds the image below along the dashed line. Which of the following squares folds onto an identical one? So we have this number 2024 made up of different tiles, and we're folding it along this dashed line, and we're trying to see which square tiles match with the square tile they're folded on top of. So let's imagine folding this direction. There are only 2 rows above the dashed line, which means that it would only match with 2 rows below the dashed line. So our third row is out of the option. So now let's look column by column and see if they have any matching tiles to begin with. If they do have matching tiles, then let's check to see if they fold on top of each other. And if they do both, then we found our answer. So this column has 2 light gray squares, but if I were to fold it, this light gray square would fold on top of this black square, and this with empty space, so it is not this column. This second column has 2 stars, so they match. However, this star would fold onto empty space, and this star would fold onto this empty space, so it is not this column. Our next column has 2 diamonds, but since they're on the same side, when we fold them, we'll have 1 diamond here and 1 diamond here, so they wouldn't match with themselves. Now, for this next column, we have 2 diamonds, and when I were to fold this tile would overlap on this tile, so these 2 tiles work. But let's check to see if we have any other options. So we only have 1 circle tile over here, and the rest is empty space, so that's not possible. In this column, none of the tiles match, so that's not possible. Same for this column. This column has 2 light gray tiles. However, this tile would overlap blank space and this on this blank space. This column has 2 circles, but again, are on the same side. So when I were to fold them, I'd have a circle here and a circle here. And so they're not overlapping with identical tiles. This column has 2 stars, but when I fold it, this star will come over here, and this star will match with this black tile. So it is not this column. This column only has 1 tile, and the black tile does not match with the empty space. Here we have 2 black tiles, but this black tile would fold on this light gray tile, and this square tile will fold on the other black tile. So it is not this column. So that means the only 2 tiles that folded onto each other and were identical are these 2 diamonds. So our answer is B. Number 2. The picture shows the first few squares of a hopping game. Every 4th square in the game has the same image in it. Mia is playing the game. On which of the following squares will Mia land only on her right foot? So here we have our hopping game. It's 2 feet, left foot, 2 feet, right foot, and then a repeat, and so on. And we want to know which of these answer choices will Mia land on her right foot. So over here we see that the 4th square is Mia on her right foot. And now this pattern repeats every 4 squares, which means number 8 would be a right foot and so on. That means that any number divisible by 4 would be Mia landing on her right foot. So let's look at these options. 10 is not divisible by 4. B, 15 is not divisible by 4. C, 20 is divisible by 4, so let's keep that. D, 22 is not divisible by 4. And E, 23 is not divisible by 4. So our answer is C. Number 3. Sasha created secret symbols for the English alphabet. He writes basil as 5 symbols and red as 3 symbols. How does he write bread? So one thing to notice is that basil has 5 letters and is written in 5 symbols, which means each letter corresponds to a symbol. Same for red. Red is 3 letters and made up of 3 symbols. Each letter is a symbol. So let's translate bread in English to Sasha's secret symbols. So the first letter B is the first letter of basil, which means the first symbol. So it's a circle with a dot inside. And looking at our answer options, the only one that starts with a circle, and a dot inside, is C. So our answer is likely C. However, we'll still write out the rest of the word to check and make sure. So for R, that's the first letter of red, which means the first symbol, which is a circle with a dot inside, and then a semicircle and another dot. For E, that is the second letter of red, which is these two triangles. For A, that is the second letter of basil and this U. For D, that is the last letter of red, which is these three lines. And checking with C, we have circle, circle and semicircle, triangles, U shape, and three lines. So our answer is in fact C. Number 4. Which of the strips should be placed in the rectangle in the picture so that each child is holding a different kite? So let's draw in each of the options. For A, we have these lines. So this child, if we follow the line, is connected to this child, and these two kites are connected to each other. And since neither of the children are holding a kite, let alone a different kite, A is not our answer. Now let's draw in B. Here, the second child is not holding a kite or connected to anything at all, and this kite isn't connected either, which means that B is not our answer. Drawing in C, we can see that the children are connected and the kites are connected, and there is no way that the kites and the children are connected because there's this gap of space between them. So C is not our answer. Drawing in D, over here, we follow the line. We see this child is connected to this kite over here, and this child is connected to this kite. So this works. Still, let's try our last option. For E, we have these lines, which means that the two children are connected and the two kites are connected, meaning that E is not our answer. So our answer is D. Number 5. Dina set up 3 bricks on the floor behind a wall. From the front, the bricks look like the figure on the right. What do the bricks look like from the back? So we're imagining if we were to turn this around, what would this look like? And let's note that this over here on this side is the same as what this is on this side. So that's one big brick behind this brick. And if we were to turn it around, whatever is behind will be in the front, and whatever's in the front would be behind. Looking at our options, we can automatically rule out D because when looking from the back, the wall would be the last thing in the very back we would see, not the front. Now, if we were to look from the back, that would mean that imagine turning this around. So like this. And that means that this brick, this darker shaded brick, would be, instead of the right, it would be on the left, which means that we can rule out A. Now, for the rest of the options, let's see. These two are similar, but vary in the height of this brick over here. These two look similar in height, while this one is much taller. And if we look at the original picture, this one is significantly more taller than this brick, so we can rule out our option E. Now between B and C, we have this brick in front, which would mean if we turn it around, it would be behind, whereas here, this larger brick, the wider brick, is behind this brick, but in front of the wall. Now, seeing here, that wider brick is behind this other brick, which means that it would be in the front when we turn it around. So we can rule out C and say that our answer is B. Number 6. Mona wants to draw the figure shown without lifting her pencil from the paper. The lengths of the 3 segments are given. What is the shortest total length she could draw? So in order to draw this figure on the right, she would have to draw one of the lengths twice because she can't pick up her pencil. So imagine doing that. You would want to do the shortest length twice because we want the shortest total length. So she would repeat this 1 centimeter length twice. So it'd be like she draws the 3 centimeter, the 1 centimeter, the 1 centimeter again, and then the 2 centimeter. And she could have started on the other end, but it wouldn't really matter because the length is the same. So we'd have a 3, 1, 1, and 2. And if we add that all together, we get 7 centimeters, which means our answer is B. Number 7. There are 2 concentric wheels, each marked with 7 positions. The wheels spin in opposite directions, and each makes a complete turn in 7 minutes. At the end of each minute, each letter lies exactly in front of a number. The picture shows the first 2 positions of the wheels, and we can see that initially letter A is in front of number 1, letter B is in front of number 2, and so on. The wheels turn until letter C is in front of number 2. Which number is letter F in front of at that point? So here we have our wheel. We have the larger wheel with the numbers and the smaller wheel with the letters. And we want to know when we keep turning them until C matches with 2. So instead of this being a 3, it'd be a 2. We want to know what number would be in front of F. Now, most of the information given isn't exactly needed. All we needed to know was that C aligns with 2. Because then all we have to do for that is move this wheel one time clockwise, which means this would be a 2, this would be a 3, this a 4, and this 5. And since we wanted to know what F would be, here we know it's a 5, meaning our answer is C. Number 8. There are 6 boxes on a truck as shown. A worker puts them on the floor. He takes 1 box at a time, but only takes a box if it does not have another box on top of it. He places this box on the ground or on top of another box. Which of the following stacks could he not build? So let's try each option. First, for A, he puts down box E at the bottom. Then he puts box F, then C, then D, or then A, then B. So this structurally could be built, which means that A is not the answer we're looking for. Moving on to B, let's say the first box he puts is an E, then an F, then a D, then C, then A, then B. So this is also possible to build, meaning B is not our answer. Let's try C. First he puts an E, then the F, then C, then A. Now, the next box he would have to take is a D because he can't put a B down without taking the box D off. However, the B is below the D in this case, which means the B, box B, was put before box D. So this is not possible to make. So C is likely our answer, but let's look at our other options. So now for option D, first let's say he puts box F, then box E on top of F, then on the ground C, D on top of C, B on top of C, and A on top of E and D. So this stack is possible to build, meaning that option D is not our answer. Now for E, let's say he puts F down, then E, then D on top of F, then C on top of D, B on top of E, and A on top of B. So this is also a possible stack to build, meaning that our answer is not E. So that means our answer is C. Number 9. Peter has a package weighing 445 grams and the following 8 weights: 500, 2 200s, 100, a 50, 2 20s, and a 5. He puts the package on a scale, as shown. What is the smallest number of weights he needs to balance the scale? Now let's note that it says balance the scale, which means that we're not trying to add up weights on the left side to equal 445, because we can add weights to the right side as well. So the easiest way we can do this and balance the scale is put our 500 weight over here. and then get this to add up to 500 as well. So here we would need 55 more. So we can put a 50 and a 5. And then both sides are 500. So our scale is balanced. And here we used 3 weights. So our answer is B. Number 10. The rooms in a hotel are numbered in ascending order, starting from 1. No number is omitted. Kangaroo counted all the digits in the room numbers and found the digit 2 14 times and the digit 5 3 times. What is the largest possible number of rooms in the hotel? So, since we know that the digit 5 was found 3 times, that means we have a room 5, we have a room 15, and we have a room 20, but not a room 35. So that means that our number of rooms is greater than or equal to 25, but less than 35. Because then there would be 4 5s, and that doesn't fit our criteria. So we can automatically rule out E and D because those numbers don't fit this. Now, we know that Kangaroo found the digit 2 14 times, so let's list the numbers with 2's. So we'd have 2, 12, and then all the numbers in the 20s. So we have 20, 21, 22. And this one's a tricky number because they said digit 2. So that means this number actually counts for 2 digits because it's got 2 2's. 23, 24. So right now we're at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So the largest possible number of rooms would have to be somewhere in between 32. So it's going to be greater than 32, but less than 42. Because if it reached 42, then we would have 15 2's. So considering both of these, that means that our x is greater than 32 and less than 35. And since we want the largest possible number, that would mean that x is 34. So our answer is C. Number 11. 2 identical rectangles, each with an area of 18, overlap to form a new rectangle as shown. The new rectangle can be divided into 3 identical squares. What is the area of the new rectangle? So since it can be divided into 3 identical squares, we see over here this line is with half of a rectangle, which means this is 1 rectangle plus half of a rectangle. So the area of 1 rectangle was 18, and the area of half a rectangle would be half of 18, which is 9, and 18 plus 9 is 27. So our new area is 27, which is B. Number 12. Mark had 5 boxes of chocolates labeled A, B, C, D, and E. The chocolates in the boxes have been given numbers according to their flavor, as shown. He ate most of the chocolates. The picture below shows what was left. What was the label of the box marked X? So over here, we see that A is the only box that has a 1 in it, which means that this box with a 1 in it has to be A. Now, that A is out of the option. The only other box with a 2 is B. A had a 2 in it as well, but since we know that this box over here is box A, that means this box cannot be box A. So this must be box B. And using that same logic, box C is the only box left with the 3. This must be box C. Box D is the only one left with a 4, so this must be box D, meaning that the box marked X is E. So our answer is E. Number 13. Rosa draws several identical rectangles to make the following picture. The width and the height of the picture are 45 centimeters and 30 centimeters respectively. What is the area of one rectangle? So we know that the width is 45, so this whole length is 45. And since they all share the same length over here, that means that there's 5 rectangles here, so 5L equals 45. Dividing by 5 on both sides, we get 9, which means that the length of this rectangle is 9. Now we know that the height is 30, so going from here to here is 30. So this is the width of each rectangle. We've got the length here. So that's saying kind of the width here. So 2L plus 3W equals 30. So since we already know that L equals 9, 2L here is 18, 2 times 9, plus 3W equals 30. Subtracting 18 from both sides, we get 3W equals 12. Dividing by 3 on both sides, we get W equals 4. So the width is 4. Meaning the area of a rectangle would be 4 times 9, which is 36, making our answer E. Number 14. Each of the 16 circles shown contains a number. Numbers in neighboring circles differ by 1. One of the circles contains the number 5 and another one contains 13. How many different numbers are written in the 16 circles? So since the numbers differ by 1, that means to go from 5 to 13, we'd have to keep increasing them by 1, and we'd have to do that on both sides of the 5. So let's say that that is the 5, and we've got 6, 7, 8, 9, 10, 11, 12, 13, right here. And on the other side, we'd have to do the same since they can only differ by 1. So this is also 6, 7, 8, 9, 10, 11, and 12. They meet perfectly at 13. And we want to know how many different numbers we wrote. So we wrote all the numbers between 5 through 13, which is 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers, making our answer A. Number 15. The diagram shows 2 large squares with the same area. Part of each square is shaded, as shown. In the first square, the midpoints of adjacent sides are joined. In the second square, 4 smaller squares, all with side lengths equal to a third of the side length of the larger square, are shaded. The area shaded in the first square is 9. What is the area shaded in the second square? So we know these are midpoints of each side, which means that if I were to cut this way, that means this triangle here is equal to this triangle here, meaning our shaded area is exactly half of our total area. And since our shaded area is 9, that means the total area is 18, which means since both of these squares have the same area, the total area of this is also 18. And since we know that the length of these shaded squares is a third of this total, that means if we were to cut this up into ninths, we have 4 shaded squares, so 4 out of 9 times 18 to find the area of the shaded squares in the second square. So we multiply this out, getting 8. So our answer is 8, which is B. Number 16. The Braille system is used by people who are blind. When written down, the digits 0 to 9 are represented by a set of black and white dots, as shown. How many different 2-digit numbers contain exactly 5 black dots? So in order to do this, there are 4 different ways we can have a sum of 5. We could do it 1 plus 4, 2 plus 3, 3 plus 2, or 4 plus 1. And we can't do 0 plus 5 or 5 plus 0 because none of these numbers have 0 black dots or 5 black dots. So let's try each case. First, for 1 plus 5, we have exactly one number that has one black dot, and that is 1. And for 4 black dots, we have one number, which is 7. So there's only one way to have this combo. Now moving on to the 2 plus 3, we have 0 as a 3, we have 5, 3, 9, and 2, so that's 4 numbers that have 2 black dots. And we have 0, 6, 8, and 4 for 3 black dots. So 4 times 4, that's 16. So we have 16 ways for this. Now for 3 plus 2, it's very tempting to say it's the same as 2 plus 3. However, since 0 is a number that has 3 black dots, we cannot put that in the tens place because then it's not a new number. So instead of having 4 numbers, we now have 3 numbers with 3 dots that would fit the criteria. And we have still 4 numbers that could be put in the ones place. So now we have 12 ways. And moving on to our last 4 plus 1, number 7 is the only one with 4 black dots, and 1 is the only one with 1. So that's one way. Now we just total up our answers, and we get 30 ways. So our answer is 30, which is C. Number 17. The figure below shows a honeycomb with 16 cells. Some of the cells contain honey. The number in each cell indicates how many of its neighboring cells contain honey. 2 cells are neighbors if they share a common edge. How many cells in the honeycomb contain honey? So our strategy for solving this would kind of be like playing Minesweeper. You would look at the number on the cell and see, based off of it, how many cells that surround it have honey in this case. So since this is 0, that means these 2 cells it shares an edge with do not have honey. However, let's look at this 3 over here. This 3 shares an edge with 4 cells, but one of them guaranteed does not have honey, which means automatically all the other 3 cells it shares an edge with do. So that 2 was having honey, the 3, and the 0. Moving on, let's see. Let's do the 2 down here. We already know that this 0 and this 3 have honey, so that means it already shares an edge with 2 cells that have honey. So this 3 cannot have honey. Now let's look at this 3 over here. It shares an edge with 6 different cells, but 3 of them do not have honey, which means the other 3 do. So these 2 4s have honey. Now let's see. This 2 over here already shares an edge with this 4 and this 3 that do have honey. So this 2 does not have honey. This 2 over here shares an edge with this 2 and 4 that do have honey. So this 2 does not have honey as well. This 4 shares an edge with 2 cells that do not have honey and is surrounded by 6 cells. So the remaining 4 cells must be the 4 cells that contain honey. So this 3 guaranteed has honey. Let's see. This 2 over here shares an edge with this 3 and 4 that do have honey. So this 3 does not have honey. Down here, this 1 shares an edge with this 4 that has honey. So this 4 does not have honey. This 4 over here shares an edge with exactly 4 cells, which means each of the cells it shares an edge with have honey. This 2 over here shares an edge with this 3 that has honey, and 2 of the other cells that it shares an edge with do not have honey. And since it only shares an edge with a total of 4 cells, this 1 must have honey as well. Now let's count the number of cells we have that contain honey. So we have this 1 over here, this 2, this 3, this 4, this 1 down here, so that's 5, this 4, so that's 6, this 3, 7, this 2, 8, and our original 0, 9, making our answer C. Number 18. Annie wants to place the numbers 1 to 10 in the circles in the diagram with one number in each circle. She wants the sum of the numbers in any 4 circles that are in a straight line, for example, the 4 gray circles, to be 23. What number must she place in the circle with the question mark? So if the sum of, say, all these circles is 23, and the sum of all these circles is 23, and these are 23, if we were to add up 23 3 times, or multiply it by 3, that is 69, but it counted this circle over here 3 times. So we want to know what number this is. So that means if we were to add up all the numbers 1 through 10, we would have counted whatever number this is once, but have 2 more times we would need to as well. So if we added up all the numbers 1 through 10, plus 2, plus 3, so on until plus 10, we get 55. And how we did that is adding 1 to 10, that's 11, 2 and 9 is also 11, 3 and 8 is 11, 4 and 7 is 11, and 5 and 6 is 11. So we get 5 pairs of 11, which is 55. So 69 minus 55 is 14. Now 14 divided by 2 is 7. And the reason we did this was because we said the circle would be counted 3 times, so 2 extra times, and that would be this 14. So we want to know what the number is, so we divided it by 2. And that means our number was 7, making our answer D. Number 19. Christian has cut 4 small squares from the corners of the larger square so that the remaining area is half of the area of the original square. The side lengths of the small squares are shown in the diagram. What is the perimeter of the remaining shape? So when it says here that the remaining area is half the area of the original square, that means that the shaded area is the other half. So let's find the shaded area. So this is a square, so 1 by 1, that's area of 1, 2 by 2, area of 4, 3 by 3, area of 9, and 6 by 6, area of 36. So 1 plus 4 plus 9 plus 36 is 50. And since we want to know the full area of the square, we would multiply that by 2, since that was half. So now we get 100. So we know the area is 100, and we know this is a square, which means all the side lengths are the same. So the square root of 100 is 10, meaning our side lengths are 10. Now the question was asking for the perimeter, and since this is a square, all the sides are the same, so our perimeter would be 4 times our side length, which is 10. So our answer is 40, which is B. Number 20. Ria wants to complete the puzzle shown so that each row and each column contain the numbers 1, 2, 3, and 4 exactly once. She wants to place the numbers so that the greater than and less than symbols show a correct relationship between the 2 values on either side of them. The symbols work in all directions, as shown in the example. So here we have 1 is less than 2, and here 1 is also less than this 2. and 1 is less than this 2, 1 is less than this 2. So what number should she place in the gray circle? So we'll solve our way down over there. So this number over here is less than 3, and then it has a number less than it. Now, the only numbers less than 3 are 2 and 1. But if this was 1, there would be no number less than that. So that means this is a 2 and this is a 1. Now, 3 is less than this number over here. And since each number, 1, 2, 3, or 4, can be in each row or column exactly once, and 1 is already in this row, this must be a 2. Now, 3 is less than this number over here, and there's a 2 in this column, making this a 1. 3 is less than this number over here, but we have a 2 in this row, making this a 1. From here, we can continue solving this as if it's almost a Sudoku and using that kind of logic. So here we have 1, 2, and 3, so this must be 4 to complete this row. Here we have 1, 3, 2, this is also a 4. This column over here is missing a 3 and a 4. Over here, we can't put a 4 because there's already a 4 in the row, making this a 3, and this a 4. And let's continue. Let's see. Here, this 1, we have a 1, which means this, okay. Actually, let's go to a different row. Let's look at this row. We need a 2 and a 3, which could potentially go anywhere. Let's see. Okay, this row needs a 3 and a 4. And since there's a 4 in this column, this must be a 3, and this must be a 4. This row needs a 1 and a 2. And since there's already a 1 in this column, this must be a 2, and this must be a 1. And now we've already found the number we were looking for, but let's just finish this to make sure that's correct. So this column would need a 3, and this column would need a 2. And that fits with this row as well. And that means we've found a way to make all of these numbers fit so that there's exactly 1, 1, 2, 3, and 4 in each row and column. And we got our answer in the gray circle as 1. So our answer is A. Number 21. There are 3 identical special dice on the table. What is the sum of the numbers on the faces that touch the table? So we want to figure out what number is underneath each of these dice. So since this is the same dice, just showing different sides, we can figure out what's underneath based off of the other numbers on it. So let's draw a net for that and see. So imagine unfolding the dice. This would be all the faces. So let's say 8 over here is our middle face here. The number above it is a 34, and left to it is a 22. We see a 22 over here, but it's connected to a 13 and a 17, which would mean here we would wrap this one side on this side, and this side would connect to this side. So that means that this number over here will be 13 and this 17. And this number over here on the other side of the 8 is 5. And this matches what we previously showed because here we have an 8, 5, and 13, and that matches this corner. So now that we know what our dice looks like, we can find the missing numbers. So we're looking for the face that would be opposite to 34, which means if I were to fold this up into a dice like this, if I were to have 34 here, that means an 8 here. I'm continuing in this direction downward. the face that I can't see, this imaginary face down back here, would be 13. Using that same logic, here we have 5. Now we have an 8. So we're going this way. 5, 8. This must be 22. Now we're looking for what's opposite to 17. We have 17, then 13. Going this direction, that means this is 8. And we want to know the sum of the numbers of these faces. So 13 plus 22 plus 28 is 43. Just making our answer C. Number 22. The diagram shows 4 touching rectangles. What is the area of the shaded rectangle? So we know that this length is 5 and this rectangle has an area of 45, making this length over here 45 divided by 5, which is 9. And since we know that this is 9 and this whole length is 13, this must be 13 minus 9, which is 4. And since this has an area of 40 and this side is 4, this side length must be 40 divided by 4, which is 10. And since we know this whole length is 16, while this is 10, this length here must be 16 minus 10, which is 6. And since we know the area of this is 48 and one side is 6, this other side must be 48 divided by 6, which is 8. Now that we know all these numbers, let's see what our other values are here. We know this is 5, and we know that this is 16, and we know that this is 6. So that means that this length here must be 16 minus 5 plus 6, which is 11. So 16 minus 11 is 5. So this must have a side length of 5. Now here we know that this length, this here to here, is 8, and this here to here is 4. So this must be 8 minus 4, which is 4. And we wanted to know the area of the shaded rectangle, which is going to be 5 times 4, which is 20, making our answer E. Number 23. The figure shows the plan of the 7 train routes of a small town. The circles indicate the stations. Martin wants to paint the lines in such a way that if 2 lines share a common station, then they are painted with different colors. What is the smallest number of colors that he can use? So another way to look at that is that instead of lines that share a common station are different colors, since we're using the least number of colors, we can say lines that don't share a station are the same color. So let's look for some lines that don't share a station. Here we see 4, 5, and 6 are all parallel, which means they don't intersect. So they can all be one color, say red. So we've used one color now. Here we notice 1 and 3 are also parallel, meaning they never intersect and can be the same color. So let's use green. So that's our second color. Now our remaining 2 stations are 2 and 7. Here we have 2, and here we have 7. Neither of them meet, so they can share a color as well. So let's have them be blue. So that was 3 colors. So we managed to have all of our 7 routes in 3 colors, making our answer A. Number 24. Damien wants to fold the net shown to make a cube. He wants the triangles that touch the edges of neighboring faces of the cube to be shaded the same. How should he shade the triangles of the unshaded square in the net? So let's look at this side that this square is connected to right now. These triangles are shaded, meaning these triangles will also be shaded. So let me fill them in here. Now, if we were to fold this up, this side over here would share this side over here. So this triangle would be sharing side with this triangle, and since this is shaded, this would be shaded as well. However, since this triangle is not shaded, this triangle would not be either. Now let's look at this side over here. This side would be connected to this side over here. So this triangle, imagine all the way it's being folded to this triangle. And since this is shaded, this would be shaded. This triangle would be connected to this triangle, which is not shaded, so we'll leave that unshaded. Down here, this would connect with this side. So if we were to fold this up, this triangle over here would connect to this triangle, which is shaded, so we'll shade this one as well. But since this one is not shaded, we won't shade this triangle. So we're looking for a square that looks like this. So all of these triangles have been shaded, and this triangle, and this triangle. So we have 5 shaded triangles and 3 unshaded triangles. And the one that fits our image is B. So our answer is B. Number 25. Simon takes 4 cups out of the cupboard and puts them randomly on the 4 saucers. For each cup, there is exactly 1 matching saucer. Which statement is correct? So let's go through the 4 or 5 statements one by one and see if they're true or false. So A, it is certain that none of the 4 cups stands on its matching saucer. And we're not certain of that because they each have a matching saucer and we weren't told there was anything stopping them from being on their corresponding saucers. So A is false. B, it is certain that exactly 1 cup stands on its matching saucer. And I mean, that's not exactly true because, say, what if this cup was on the striped saucer and the squares was on the polka dots, and the stripes were on the dots, and the dots was on the squares? So each cup is on a different saucer than the one that matches it. So that would make B false. Now C. It is impossible for exactly 2 cups to stand on their matching saucers. Let's see. We put the polka dot on the polka dot and the stripe on the stripe, but then we put the square on the dot and the dot on the square. So we have exactly 2 cups on their matching saucers. So that means that C is incorrect. D. It is impossible for exactly 3 cups to stand on their matching saucers. So let's put the polka dot on the polka dot, the stripe on the stripe, the other dot on the other dot, and then we have a square mug and a square saucer, and there's nothing we can do to not make them match. So far D is true. So let's continue. For E, it is impossible for all 4 cups to stand on their matching saucers. Since each of the 4 cups has a matching saucer, and we weren't told of anything stopping them from being on their matching saucer, that is false. We could match them, making our answer D. It is impossible to have exactly 3 cups stand on their matching saucers because then the 4th cup would have to be on the 4th saucer, which is its matching saucer. So our answer is D. Number 26. Mary wants to write numbers 1 to 8 on the vertices of a cube. She wants the sum of the numbers on the vertices of each face to be the same. She has already written the numbers 6, 7, and 8 as shown. What number should she write on the vertex marked with the question mark? So we know the sum of the numbers on these vertices of each face are the same. So if I were to add up all of these dots, they would be the same. And if I were to add up all of these dots, they would be the same. So if I were to add up all the numbers 1 through 8, I should get the value of these 2 faces added up. And all the numbers 1 through 8 summed would be 36. So 36 is this face plus this face. And since both the faces are equal, if I divide 36 by 2, I should get the sum of each face. So the sum of each face is 18. So let's start solving for the vertex. First, let's do this face over here. So we know that 8 plus 7 plus the sum of these two, so let's call that x, equals 18. So that means 8 plus 7 is 15, so we subtract 15 from both sides. X equals 15. And since each of these numbers are different, we don't have any zeros, our two numbers must be 1 and 2. So this could be 1 and 2, or this can be 2 and 1. That would depend on this face. So let's go down to this face. Here we have 8 plus 6 plus, say, y equals 18. And 8 plus 6 is 14. So subtract 14 from both sides, and we get y equals 4. Now, the ways to do this would be 0, 4, but there's no 0, 1 and 3, and 2 and 2. But we can't repeat a number, so 1 and 3 is the only way. And since we have a 1 in both of these, this number, this corner that they both share, must be 1, and this must be 3. So the question mark is a 3, which means our answer is C. Number 27. A grandmother has some candy. She decides to divide it up amongst her grandchildren so that each has a bag containing the same number of pieces of candy. She puts the largest possible number of pieces of candy in each bag. When she's done, there are 20 pieces of candy in each bag and 12 pieces of candy left over. What is the smallest number of pieces of candy she could have? So we know that she had some original amount of candy and she divided it by some number, and she got 20 with a remainder of 12. And since we want her to have, like, originally had the smallest amount of candy, that means, let's say, since we had a remainder of 12, it has to be greater than 12. So let's say 13, which means if she had one more grandchild, then or actually one less grandchild, then they would have all got another piece of candy. So we want to know the amount of candy she started off with. And since she gave 20 pieces of candy to each person, we do 20 times 13, which is 260. And that's a 6. And then we'd add our remainder of 12 to that and get 272. So she started off with 272 pieces of candy, making our answer C. Number 28. Dan plans to cut a rope into 12 equal pieces and marks the points where he needs to cut. Muhammad plans to cut the same rope into 16 equal pieces and marks the points where he needs to cut. Then Maya cuts the rope at all the marked points. How many pieces does Maya get? So let's draw out our rope and see Dan cut it into 12, so he'd cut here. So this is fourths, and each fourth is cut into thirds. And let me make the fourths a little bigger. However, not Dan, Muhammad would have cut that into 16 pieces. So that would have been cutting into fourths, and then cutting the fourths into fourths. And the thing to note about this is that they both would have cut into fourths. So let's see, for 1/4, Dan would have cut it twice into 3 pieces. And Muhammad would have cut it 3 times into 4 pieces. So when Maya cuts this, she would have to make 5 cuts, and so this would end up in 6 pieces. And that's per fourth. So we would multiply that by 4 and get 24. So our answer is A, 24 pieces. Number 29. Emma is playing with the 7 caterpillar puzzle pieces shown. She wants to build a caterpillar that has 1 head, 1 tail, and 1, 2, or 3 puzzle pieces in between. How many different caterpillars can Emma build? So here we have 2 head pieces, we have 2 tail pieces, and we have 3 body pieces. And the thing to notice is that this has a square connecting piece, while these two have the circular connecting pieces. These circular connecting pieces connect to these front parts, while the square connecting piece connects to the tail parts, meaning that this cherry will always be there in the body because that's the only body piece and the only piece in general that can connect to these tails. So let's see the different caterpillars Emma can build. First, let's try a caterpillar that has one body. So she can pick between 2 different heads. And since we're only doing one body, she has to choose the cherry one, so that's 1. And then she can pick between 2 different tails. So that's 2 times 1 times 2, which is 4 ways she can build a caterpillar with one puzzle piece as a body. Now, if she was to choose 2 pieces to be in between, then we'd have 2 times, and then for the 2 different pieces, the first piece could be the apple or the grape, so that's 2, but then the second piece has to be the cherry, so that's 2 times 1 times 2. So 2 times 2 times 2 is 8 ways. Now for 3 puzzle pieces, the head can be 2 different options. The first can be either the apple or the grape. The second would be whichever one we didn't pick. So if we pick the apple, then it's the grape, so it's 1. And then the cherry, and then 2 different options for the tails. So again, 8 ways. And the total number of caterpillars Emma can build is, if we sum this all up, which is 20. So our answer is Emma can build 20 different caterpillars, which is E. Number 30. Ava writes a 3-digit number on the whiteboard. Then Brandon writes a 4th digit to the right of the previous ones. He says, "Look, the number increased by 2024. What digit did Brandon write?" So let's say Ava's original number was A, B, C, and then Brandon put a letter D, or number D, behind it. So we want to know what D is. So let's write this as equations. So we know that ABCD is equal to 10 times ABC plus D. Oh, that's D. Okay. And we also know that ABCD equals 2024 plus ABC. So let's substitute 10 ABC plus D for ABCD. So we have 10 ABC plus D equals 2024 plus ABC. So we subtract ABC from both sides. Now we have 9 ABC plus D equals 2024. And we know that D is a single digit. So if I were to divide both sides by 2024, my remainder would be D. So let me do that. So when I'm dividing 20 divided by 9, you can do 2 because of 18, remainder 2, so now 22 divided by 9, again 18, and now this time you got 4, so 44 divided by 9, that would be 4, and have a remainder of 8. And since we said D is a single digit, our remainder would be D. That means D equals 8. So our answer is, ironically, D. Thank you for watching this. Good luck with Math Kangaroo, and goodbye.
Don't forget to subscribe and like. If you have any questions, you can email info@agoramatrico.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website